In this video, we will show how the GAL framework for the NetFPGA platform works. First of all, we should observe that the GAL exposes 7 commands: the discovery, monitor state, monitor consumption, provisioning, release, commit, and rollback. The very first step to do is to send the discovery command to the root resource. 0 is the ID of the root resource, and the second parameter is the committed parameter, that is 1 or 0. In this case we set as 0. As you can see from the CLI, only the logical resources are shown, and their IDs are in the range from 0.0.5 to 0.0.8. The description of each resource contains the correspondent IP address associated to the logical resource. Let's notice that the physical resources are not shown, but in the specific case of the NetFPGA platform, they are accessible in the read-only mode. We can send the discovery, monitor state, and monitor consumption commands to observe the current behavior of the hardware. In particular, the Xilinx Virtex2 Pro physical resource has the ID 0.0.0, and the hardware ports have the IDs in the range from 0.0.1 to 0.0.4. As far as the hardware on the NetFPGA is concerned, we are able to change only the clock frequency of the FPGA chip, choosing from 5 different rates. The state 0 of the chip represents the state with the higher quality of service, whereas the state 4 represents the state with the maximum energy saving. Using the command monitor state 0.0.0, I'm sending the monitor state command to the FPGA physical resource in order to know the current state of the Xilinx Virtex2 Pro. The current state is 0. The discovery command shows also the entity dependency list as optimal power state. The monitor state command shows the current state of an entity. As you can see from the CLI, all the logical resources are currently into the state 0. The provisioning command sets the state of an entity to the specified state. The logical resource of the NetFPGA have 5 different states, from 0 to 4, that are related to the FPGA hardware states mentioned before. Within the NetFPGA platform, if we want to guarantee the required quality of service for each logical resource, we have to apply the following policy. For each possible combination of states configuration, the FPGA chip must be put in the minimum state between the states set to all the logical resources. So, for example, we can provisioning to the 0.0.5 resource the state 1, and so 0.0.6 the state 2, and to this logical resource 0.0.7 the state 3, and to the 0.0.8 the state 4. As we said before, the state 1 has to be set on the CPU when we will send the commit command. Looking at the output of the monitor state 0.0.0 command, you can notice that the state is still the same. Performing the commit command to the root node, the FPGA chip is put to the state 1, that is the minimum of the states provided to the logical resources. The release command set the entity to its default state. As far as the logical resources are concerned, their default state corresponds to the state 0. as we can notice from the monitor state of the CPU, we can see that the current state is 0. The rollback command is the opposite of the commit. It allows to reset the provisioned state of the system to the last committed configuration. The current state of the CPU is 0, and sending the provisioning command to all the logical resources, setting to the state 3 them, and sending the rollback command if we commit the current configuration. We can notice that the state of the system of the FPGA chip in particular is still 0. It remains as exactly the previous one. Besides the state from 0 to 4 discussed before, all the logical resources are characterized by the autonomical state, the state 5. If all the logical resources are set to the state 5, the system works in autonomical configuration. It changes autonomically the clock frequency according to the overall bit rate of the 4 Ethernet ports. Now I'm going to commit the current configuration, and I'm going to monitor the power state of the CPU, that is the lower one, the state 4. If we send some traffic, for example with a rate of 320 megahertz for each port, this is the window of the packet generator. If we monitor the current state of the FPGA chip, we can see that the current state now is 3. We can stop the traffic and send another flow of traffic with 400 megahertz. In this case, if we monitor the state of the chip, we can see that the current state is 2. If we stop the traffic again and send a new flow of 500, we can see that now that the state is 1, and if we send another flow of 800 megahertz, we can see that the current state of the chip is 0.